general relativity, step by step. We've derived this rather beautiful result here for motion along a non-null geodesic, a world line of a geodesic particle, a particle moving along a geodesic. So we're going to go back to, what value of G alpha beta we're going to use. It's perfectly general so far, but of course my interest at this point is doing the same calculation, 2m over r dt squared minus, sorry, it's plus dr squared over 2m over r plus r squared d theta squared plus r squared sine squared theta d phi squared. And I'm going to say that 2m equals 1 because it drives me absolutely crazy. ds squared equals minus 1 over r dt squared plus dr squared over the same thing plus the other terms. Okay, so where does that leave our Lagrangian? Remember that what we're trying to do here, we're looking at d2x mu by d tau squared. That's the affine d tau squared. Tau is the wristwatch parameter, plus these rather complicated dx mu by d tau dx, what's mu, the variable, rho by d tau equals 0. Rather complicated. That thing there is a complete beast to handle. So what I'm going to do is I'm going to use this expression here. You remember that the Lagrangian, the function that I'm using, the L, is just going to be equal to G alpha beta x dot alpha x dot beta. So I'm just going to evaluate it and just use the Euler-Lagrange equations. Okay, so let's just do that then. So there's my metric tensor here. May as well write out all the terms. What the hell? What have we got? We've got r squared d theta squared plus r squared sine squared theta d phi squared. And of course what I'm going to do is set theta equal pi by 2, so I'll just consider it equatorial motion. So what happens to my Lagrangian? Well, that equals minus 1 over r, which is this term here, t dot squared. Remember, the dot is differentiation with respect to wristwatch time, not coordinate time, plus 1 over r dot squared, plus the other terms, r squared theta dot squared plus sine squared theta phi dot squared. Is it a phi or a psi? That's a phi. I always get that one wrong. And that's my L. Now, what equations have I got? What I want to do is to solve the Euler-Lagrange equations, which is d by d tau, di L by di x dot mu minus di L by di x mu equals 0. How long has this one been going? 3 minutes 37. Well, you see, you've got 4 equations here. You've got mu equals t, r, theta and phi. So it looks like it's one equation, but there's actually 4 equations here. So what we're going to do is do them step by step. There we go. Let's try the t. Let's try the t. d by d tau of di L by, well, let's write it out, di L by di t minus di L by, oh no, it's di L di t dot, isn't it? T dot, which is this term here, of course, minus di L di t equals 0. And straight away we can see, because we've got a steady system, that that is equal to 0. So that tells me that d by d tau of dl by dt dot equals 0. So all I need to do is to differentiate this beast here, and we can do it. So that's just telling me that t dot, no, let me write out the whole thing. It's instructive to write it out. D by d tau of dl by dt dot. So that's just this term here, 2 t dot 1 minus 1 over r equals 0. So that tells me that t dot 1 minus 1 over r equals a constant k. That's nice. That would have been a lot more effort to have achieved by going through this thing here. We may as well use the Euler-Lagrange equations because they give us the same answer in so much of a nicer way. And it's a more pleasing, a nicer, more clean, nice way of doing it. Okay, well there's my equation. I'm going to, yeah, this has already been 6 minutes. I'm going to stop there. Stop.